Okay, I think it's recording. So, we're going to look at the end of, this is question 2 from the 2017. All the rest of the questions we're going to look at for this test are pretty short. And let's see, we'll meet Monday, Wednesday, Friday, and as of now, we'll just say 10:30. I may adjust the times again. It'll always be sometime between 9 and 11, but we're going to shoot for 10:30. So, okay, here's the question, and it shifts into reaction rates in kinetics. It says the ammonium salt of isocyanic acid is a product of the decomposition of urea, represented below. So here's urea. It says a student is studying the decomposition reaction, and they run a reaction at 90 degrees Celsius. They collect the data below on the concentration of urea as a function of time, as shown in the data table and the graph below. So they started at, let's review this. They started at 0.1, and what's the units on that?
Molar.
Molar, yep. Since I've got brackets, that's got to be in molar. So they start at 0.1. By the end, they're down to approximately 0.1 molar. And the student proposes that the rate law is K times the concentration of urea to the first power. Okay, explain how the data supports the student's proposed rate law. So we're on question EI. So how does that support the proposed rate law? So actually, I shouldn't have written the 1. First of all, you identify its first order, and then how does the data line up with first order? What would you justify it with?
That the concentration of urea is based on the rate of change is based on the concentration of urea.
Yep. Concentration affects rate. But hey, that's not quite enough because that could be first order or second order. So you have to justify that it's first order.
By positive.
Wouldn't the change of rate would always be the same?
Yeah. Well, no. Let's see. The second derivative. Yeah. So Evan, you probably would. You're correct, but I would bet the typical AP chemistry grader would probably not understand that. That would be the math answer, which is 100% right. But the chemistry answer has to do more with stuff that we talked about. So we talked about, maybe you and I talked about second derivative, but everybody else in AP chemistry probably only talked about things like reaction rate, changing rate, half-life. So how does this relate to half-life?
Oh, I see.
So if you look in the first 10 minutes, what happens to the concentration?
Half of it's gone.
Half of it's gone. Yep. In the next 10 minutes, from 10 to 20, half of that's gone, and then half of that's gone. So you need to say something about the half-life remains constant. And that only happens for first order. Okay.
Wouldn't that also happen for 0th order?
No, 0th order, the half-life the half-life, so to go from 0 to 0.5 is different. It's not the same, because check this out. If it was a straight line in the first what is that, 10 minutes? In the first 10 minutes, you've only gone down maybe 20%. And then the difference from here to here is actually a bigger percentage because it's a smaller value. So the percent doesn't change. For first order, it's always 50%, 50%, 50% on the half-life. And for second order, it actually, the rate's changing, or sorry, the half-life is changing too. So the only one where we should talk about something called half-life is a first order reaction. Okay, using the proposed rate law and the student's results, determine the value of the rate constant K. So there is one equation, and it only works for first order, and it says the half-life is equal to 0.693 over K, and that 693, that comes from the natural log of 1/2. Okay.
Yep.
So you're going to plug in the half-life, which is, what is the half-life of this?
Let's say 10 hours.
10 hours. So I'd say 10 hours equals 0.693 over K. So K equals, just do your little switcheroo, 0.693 over 10 hours, which equals 0.0693. And what units go with K?
None.
Ooh, good. So that
No, it's weird.
it's weird. Now, hey, big thing, capital K, which is for equilibrium, right? So I should put KEQ. That has no units.
Oh,
Little k, which is called the rate constant. Arthur's right. Arthur says it has weird units and it depends on what order it is. So for this case, you look at this equation right here. Now, and you're like, okay, you're like the 693, the 0.693 on top, that is unitless. But since you used hours on bottom, that has a unit in it.
1 over hours.
So it's
right?
so it's 1 over
Reciprocal hours.
Yep,
Oh,
reciprocal hours. So big thing to remember. Well, you need water, Linus? Oh, okay. Mama's home. Can you go pause the video and then you can find Mama.
help,
Yeah,
Dad!
it seems like you're.
I'm dying.
Well, here, let me
It
get
sounds
Linus
like
some
your
water.
kid really needs some water.
I'm dying, please.
He's watching
That was
Tom
great.
and Jerry.
A very loud shout for water.
The kid is just screaming.
He-
I had water.
he-
Daddy's father.
He has headphones on. He has headphones on, and he doesn't know how to normalize his voice when he's wearing headphones.
It's okay, Linus. Neither do I.
Yeah.
I'm just shouting always.
Yep. Okay. So moving. Okay. So that's how I would probably do it if it was asking about half-life, as I would find that equation on the sheet. And again, it only works if it's first order. If it's let me do a new page really fast. You could also solve it this way. New page. Let me go to. Oh, actually, I'll pull it up on Chrome. They're called the integrated rate laws. Let me pull this up. Integrated. Oops. Rate laws. These are also given on your rate laws. They're also given on the formula sheet. Let's see if I can find a good one that's legible. There we go. So you could use, let me open it in a new tab. So you could potentially, I wonder if I can copy and paste it. Copy. Paste. Here it comes. There we go. Make it big. So we could, if we knew that this was first order, you could like basically use this equation and plug it in, plug in values. So I could plug in the concentration at time t would have been, I think we said it was like 0.05 equals the original concentration, which was 0.1 times e to the negative k times 10. And then you could solve this one and you'd end up with the same answer. Just to show you, to solve for k, how would you start?
Dividing the 0.1 out.
Yep, divide the 0.1 out, which you will see, what's 0.5 over 0.1? 0.05 over 0.1.
0.005?
Isn't that a half?
0.5.
What does that reduce to? Doesn't that reduce to 5 over 10, which is a half?
Oh.
Yeah.
Okay, equals e to the negative k times 10. Well, what would you do next?
Take the natural log.
Take the natural log, yeah. And so then this all works out that you get the natural log of a half, and then you divide by negative 10. So actually, I lied. I lied up. Let me go back to my page. The negative, this comes out, the natural log of a half comes out negative. Okay, and then negative divided by negative, this does come out to 0.0693 equals K. And that would be reciprocal hours. Okay, when I was talking, let me go back to that page. When I was talking right here, I lied. 0.693 is actually the natural log of 2, not 1/2. So they're just saying that like the doubling time, and it works out with the negatives and logs, but it's in there. And this equation right here is a simplification of what we just solved, okay, using natural log. So I would just go with that, okay. But the other equation is also given on there in a couple forms. Okay, I'm gonna move on to number 3. This is another equilibrium one. Says at high temperatures, and I think we've done lots of ones involving nitrogen and oxygen from the book, and just over time, pretty much a lot of gas phase equilibrium involves oxygen. Okay, at high temperatures, N2 and O2 react to produce nitrogen monoxide as represented by the equation above. Write the expression for Kp, which is equilibrium constant in terms of partial pressure for the forward reaction. So as written, what would Kp equal? Partial pressure of NO, yep.
Squared, right?
Perfect, yep.
Divided by N2 times O2.
There you go. So that would get you a point. A student injects N2 and O2 into a previously evacuated rigid vessel and raises the temperature of the vessel to 2000. At this temperature, the initial partial pressures of P2 and O2 are 6.01 and 1.61 respectively. And then they allow it to reach equilibrium. The partial pressure of NO at equilibrium is 0.122 atmospheres. Calculate Kp. Whenever you're calculating Kp, you're going to need ice chart. So you say N2 plus O2 makes NO ICE, and you plug in what's given. So they know the partial pressures are 6.01, 1.61, and they said it was previously evacuated and had no NO to start with. Okay, and then what's the other piece of information? They say partial pressure of NO at equilibrium is 0.122, right? So NO down here at equilibrium would be 0.122. So now you should be able to solve out the rest, correct? So how'd they go from 0 to 0.122? I had to add 0.122, right? And to get that stoichiometrically, what had to happen to the nitrogen?
Subtract. Yeah.
Does that make sense? Oh, and sorry, I forgot to balance. Nope, it's not right.
Yeah, because I was gonna say.
Oops, I forgot to balance.
Oh.
So hey, this one should be twice as large as these two because of the stoichiometry. So half of that would be, what's half of 122? 61.
Yeah.
Okay, so if I say 0.061 minus 0.061, then I can subtract, I think, here, let me just refer to the document so I don't have to subtract. Where is it? There we go. They ended up getting 5.95. They just rounded sig figs appropriately, and then 1.61 minus that guy was 1.55, and they got 0.122. Yep. So we've got all the equilibrium partial pressures now. So if you want to know Kp, you just plug them in. So Kp equals 0.122 squared over 5.95 times 1.55, and it comes out to, so you guys okay plugging in all those numbers?
Yep.
Okay, and then you end up getting 0.006, 161. Okay, which they didn't ask any other follow-up questions on that, and actually the next questions involve stuff that we've cut out of the curriculum. So I'm going to stop here. So we know that this is one unitless because all capital K's are unitless, and then we know that it favors which side of the reaction. What would you expect to find lots of? Here would you expect to find lots of N2 and O2? It would, yes, it favors the reactants, right? And you guys can see that. Doesn't equilibrium, basically those concentrations stay very high, right?
Yeah.
So we'd say that it favors the left side of the reaction. And let's see, something else I could have asked here.
If you want to move the reaction to the right, you could increase the pressure, right?
Yeah. Actually, here would be a good thing. That's a good question, Arthur. Why would pressure have no effect on changing or shifting equilibrium for this reaction?
Evan also did that.
Pressure has no effect.
Is it because when they collide, they'll separate anyways? Or
Yeah, something it has to do with probability. Look at the probability of what's happening here. So what has to happen for the reaction to go to the right? To go this way, what has to collide? N2 and O2, which is how many molecules?
2.
2. Okay. Hey, to go this way, what has to collide?
Nothing.
No, come on. Yeah, 2 NOs have to collide. Does that make sense?
Yeah.
Because it's 2 NOs coming together. So, hey, if it's 2 particles that have to collide versus 2 particles that have to collide, does that make sense that it's going to affect increasing the pressure? It's still the same number of particles that have to collide on both sides.
Yeah.
So it doesn't favor either. There has to be an imbalance in the number of moles of gas for pressure to affect it.
So if you had like all NO and all of, like, the pressure would stay the same no matter where the reaction is.
Correct. And hey, how about this? If you had something like A plus B goes to AB, okay, then increasing, and it was in equilibrium, increasing P would shift this, or would, I shouldn't say shift, it will pushes to the right. Because I have 2 moles of gas on this side versus 1 mole on this side. So an increase in pressure will always squeeze where there's more moles of gas. It'll impact that reaction rate more than it will where there's fewer moles. So it ends up pushing the reaction to the right. Okay? So that's kind of how you look at it. So pressure, you always look for where the most moles are, and it pushes it towards the opposite side. Here you go. Here's another question I could have asked. So even though pressure has no effect, let's go back to this. Because there's 2 moles of, okay, I got it. There's 2 moles of gas on both sides, N2 and O2 versus NO and NO. Which ones do you expect to find each other more easily and react to, say, like, form the products on the other side? Which ones are going to be more likely to collide, N2 and O2 or 2 NOs?
I think 2 NOs, because
2 NOs.
Doesn't it mean that the N2 and the O2 have to break apart first and then?
Okay, so hey Arthur, you're thinking mechanism, and you're correct. So maybe the mechanism favors one side versus the other, but I'm just thinking more in terms of intermolecular forces. So these things are zooming around. There is going to be some intermolecular force, either attraction or repulsions or things like that. So why would 2 NOs be more likely to find each other? How about this?
Maybe electronegativity.
Let's say it looks like this versus N2 and O2. Something with electronegativity, yeah. Let's say oxygen's more electronegative than nitrogen. Then what's that do to the polarity?
It shifts it?
Yeah.
Yeah, because the oxygen wants the electrons more.
Correct.
So it makes them
Correct. So this would be a polar molecule, right?
Yeah.
And then these would be two nonpolar molecules, nonpolar. So nonpolar molecules, right, are probably going to be, and they're all similar in size because nitrogen and oxygen are right next to each other on the periodic table. So it's not like there's one that's massively bigger than the other. So London dispersion forces will be roughly the same for all of these molecules, but the polarity, right, the pull of that oxygen on the polar molecule, this will probably be more likely to run into itself. It'll find another particle because it has like a little magnet, right?
Yeah.
And so you would say they could actually ask like which gas behaves least ideally, and you would say something like this, because ideal gases, what's true about all intermolecular forces in an ideal gas?
Ignored.
Yeah, intermolecular forces do not exist in ideal gases. Okay, so you would say, yeah. So actually, pressure would probably influence this, but assuming that they all behave ideally, pressure has no effect. Okay. We haven't talked about ideal gases, yeah, and maybe I'm gonna stop here in a second. Oh yeah, we'll go. Ideal gases, in terms of, oh geez, where was I going with this?
I don't know.
Let me think. Tenants of kinetic theory. And ideal gases. And we can, gases only has one S, right? So the tenets of ideal gases, let's just talk about what makes a gas ideal, and then we can review the van der Waals equation. We'll look at it. So no intermolecular forces, we just talked about. So what else has to be true? To minimize London dispersion forces, which shouldn't exist, what has to be true about the particle size? Or the gas size? Yep.
Yeah.
Infinitely small. So that'll basically give it no electron cloud, so it can't have London dispersion forces. They have to be
size, right?
They have to be what?
They can't have size, right?
Yep, infinitely small. So no size. They have to be behave perfectly. I know they're infinitely small, which is weird, but they have to be perfectly spherical. And they have to transfer 100% of their energy. Oops. I shouldn't say transfer. They have to retain / transfer 100% of their energy during collisions. And the physics word for that is they are perfectly elastic. Okay, so they have to bounce off each other without mushing together. There can be no deformation. This would be like the same thing throwing a ball of clay against a wall and it just mushes and all of its energy gets lost in deformation. But versus throwing a bouncy ball against a wall and having it bounce back like almost at the same speed that it hit it, and with as much energy, no deformation, and just returning all the energy in the collision. So perfectly elastic. Let's see. So those are what makes it an ideal gas, and then what conditions favor that?
Isn't it lower pressures?
Yep. Behave ideally.
Smaller molecules.
Yep, low pressure, small gas molecules.
Isn't it low heat or a low amount of temperature?
So here, let's talk. It's the opposite way, but you'll see why in a second, Keaton. So low pressure what is that? Why does low pressure make a gas behave ideally?
Less particles.
Yep, it has less neighbors. So, like, basically, no intermolecular force, like attraction to something. If there's no neighbors around it, then it can't be attracted to anything. Okay, a small gas molecule means less London dispersion force and less chance of polarity. Okay, and then high temperature. So Keaton, what would that do to the time which it spends nearby a neighbor?
Oh, very low.
Yeah.
Because it's moving so fast. I see.
Less time to interact due to high speeds. Interact. Because it's high speed. Okay. And so we know ideal gas law. This holds true if you're at those conditions. Okay.
Yep.
And then let me pull up on here the van der Waals equation. Oops. Yeah, the big equation. We're not going to solve anything with it, but just to talk, and this is where we'll stop. Van der Waals equation of state, which is, let's copy this one, open a new window. Sure, oops, crap, didn't mean to do that. Open image, a new tab, copy, paste. Big. All right, so then you can almost see here's this term, this v minus b, which is in the denominator on the right side. So I know, and here's a v squared. If you were to move those to the opposite side of the equation, it would involve some multiplication to get it up in the numerator, right? So like I could have basically, I just want you guys to see the comparison. P equals nRT over v. Does that make sense? Where I could move the v, down here.
Are you trying to show something on the screen?
Oh, is
Yeah.
it not showing?
Yeah, no.
Wait, what happened? What happened?
I think it left the meeting.
Oh, man. Oh.
So, we've
Oh,
just been
man.
hearing you monologue for the past like 30 seconds.
Okay, wait. I'm sorry.
Good. AP chemistry sounding things.
Woo!
Yep. Oh, man.
Nothing like sounding smart.
Oh, man, hold on. What just happened?
We always ask yourself.
It kicked me out of the meeting. Okay, wait, that was probably my fault.
Perhaps if you do some kind of interpretive dance to show us what you're trying to explain here.
Or you can just write it down.
No, I got this. Your entire screen share.
There's now 3 Neo4s inside the presentation.
There you go. Okay, now can you see my screen?
Yes.
All right, so you guys are good with PV equals nRT, yes?
Mm-hmm.
And you're good that you could potentially divide by V and move the V to the bottom of the other side, yeah?
Mm-hmm.
Okay, so looking at, this is called the van der Waals equation. Zoom in. So it looks very similar to the ideal gas law. You have P on one side, you have RT, and you have a volume on the other side. You don't have an N though. Okay, but and I feel like I'm missing an N. I think A has N built into it. Let me see if I've got a better equation of state, because that's killing me that it looks like that. Let's see if I've got it. Here's a better one. Copy image. This one should be better. This is how it's written. This is how AP would write it. It's not on your formula sheet, but if they happen to ask a question about it, they would write it for you. So here you go. So here's P and V, and here's nRT, and you guys can see this term right here. Typically, if we say ideal gases exhibit no volume, or they take up no volume, that would be a perfectly ideal gas, but because gases take up a little bit of space from the container that they're occupying, you subtract off. So this is called the volume correction term.
Okay.
So, and that little b, that's a constant. So which would you expect to have a higher b value? Which one would have a higher volume correction constant?
Argon.
Argon, because why?
It's bigger.
It's bigger. Yep. And then this one is called, basically, it takes your pressure, and this is called the what do we want to call it? Like pressure correction. And basically, it's gonna say that some molecules. Okay, this whole term is considered like the ideal pressure, right? And so what they're saying is the real pressure is actually got to be combined with this pressure correction factor. And so the bigger the pressure correction factor, this means it's like more polar or bigger, but I don't know what you'd call it. Stickier? Let's say stickier. So stickier items, stickier gases have a bigger pressure correction term. So like things that have very big electron clouds, or things that are very polar will have a large A value, and then things that are like very non-polar and very small will have a small pressure correction factor. So I don't know. There's probably more examples about it. This is kind of a nuance. It's like a very detailed, nitpicky thing. So I doubt they're going to put van der Waals on there, but that's what it is. So this accounts for the stickiness, and then this term corrects for how big the particle is. And
so
yeah.
The pressure correction thing.
Yeah.
Wouldn't chlorine, bromine.
No, like if the gas was, say, hydrofluoric acid versus okay, see you later, versus O2. Like hydrofluoric acid and O2, or actually, yeah, let's say they're both diatomic gases, right?
Yeah.
Yep.
And like here's HF, right? So HF, if it was in gas phase, would be, yeah, very, very polar, and it would stick to itself, or it would try to stick to itself, because, right, it could H bond. Now, hydrogen bonds don't typically form in the gas phase, but those hydrogen bonds, as molecules zoom by each other, temporarily, very quickly form and break, and this one, it's going to happen a lot, versus O2 can't hydrogen bond to itself. It can't form a dipole interaction. So yeah, this would have a big A, and this would have a littler A.
Okay, so it's like the difference of the molecule.
Yeah. And again, these are all these A's and B's. Where do they come from? Like when you look them up in a table, where did they come from?
So it was the question
from like the
A's and B's. When you look them up in your book, because you can look them up. If you look up van der Waals, it'll tell you all the A's and B's. Where do those values come from?
Oh my god.
I'm going to come from like the volume of the molecule.
Yeah, but they come from like the scientists. These are all experimental values. So it's not like there's here you go. Like, what's a good example? 1s2, 2s2, 2p6, 3s2. Where did these numbers 2 and 6 come from?
That's how many stages, or how many groups of electrons?
Yeah, and hey, that's a natural property. That's like a fundamental property in nature. Those numbers scientists didn't pick, or they didn't measure. These were not measured values. These are things that are inherent. Okay, that's what I'm looking for, the word. These are inherent properties. Okay? versus these values when you look it up in a book, A and B, and you get like A equals 0.0237 and B equals 1.8 times 10 to the minus 5. These are experimental values. Okay, they're not necessarily tied to fundamental nature of the gas. They're just something that a scientist named van der Waals has used to describe a phenomena. So they're not like a law. That's the interesting part. They're a descriptive experimental value that tries to describe what's happening. Okay, versus this PV equals nRT. That is a fundamental law. That is how gases behave. And it's
ideal gases.
Yeah, okay, ideal gases. Now, again, we use the term ideal because no gas is ideal. And scientists have projected back out, right? They've kind of seen the relationship and they know if gases were to behave perfectly ideal, they would follow this equation. So that gives us like a starting point. It's like a fundamental behavior. All it is a bunch of inverse and direct relationships, right?
Mm-hmm.
Okay, and so that's called a law, and there's no numbers in it. There are numbers in it actually. There's numbers like 1. Does that make sense?
Yep.
It's first order everywhere. Okay, well those ones, those are inherent. Those are part of nature. Okay, it's not something that we just made up or described. Okay, versus van der Waals, all these numbers down here that scientists have reported, those are just experimental descriptions. And so nobody has come up with a perfect unifying equation of state that describes exactly how gases behave. So that's like the goal of scientists, is to get to the final equation that describes everything. So I know I showed it once, but let me just type in different equations of states.
The equation that describes everything.
And we're looking for that, in a lot of areas.
Do seals have this information? Biology.
Okay, so equations of state. I wonder if I've got them here. Yeah, let's see if we can go.
I bet you Stephen Hawking knew.
Yeah, so here you go. This is just a list of scientists and their attempts to describe really what's going on. But Boyle's, Charles, Dalton, ideal gas law, then van der Waals equations of state, and then you see all these newer ones from the 1900s. The Redlich-Kwong, Suave modification, Peng Robinson, just all these different ways to describe how gases behave. And then again, they're getting into what's really crazy is all the weird forms of matter that maybe exist out in the universe. So like I think Bose, there's like the Bose-Einstein condensate. I don't know, but here's a very oh my gosh, right? Like you look at this thing, and again,
What
it's
does EXP mean?
e to the that's exp is a way to write e to the power of without using superscripts.
Oh, so e to the power of
negative r1v, correct. And so, anyways, just giving you a precursor. If you go into industry or you go work even like as a X-ray tech or a dental tech, and you're using all these cool instruments that you basically run a test and it reports back a value. Just like we were using our pH probes, and you put your probe in there in the solution and it gave you a number. Those are all those numbers that instruments report are based on some kind of an equation. And the nicer the instrument, the better the equation of state. Or sometimes you pick the equation of state that fits your situation the best. So again, it's like a tool in the toolbox now. So chemistry and all these sciences that you learn are kind of like when you take a safety course when you're going to be working in a wood shop. Okay, we just give you the basics on how to like operate and how to like not ruin things. And then the actual tools, the tool set are the equations and the software and the programs that you guys go and you use in the lab. So it's very interesting. Like, I'm just thinking more and more about this just because, I don't know, school now is weird since we're doing it online, and jobs are going to be way different after we all go back to work because we're realizing we can do our jobs differently. So I'm just saying your toolbox is going to look a lot different. So the more you practice a wide variety of things, science, math, health, I don't know, taking a computer programming class, taking a psychology class or an art class. Yeah, like everything is kind of interrelated at some point. So
Oh my god.
so
I'm gonna get an art degree.
no, please don't do that. But anyways, sorry. This is my little philosophical topic today. Is just try and do a lot of wide variety of learning because it's all valuable and it will get used somewhere. Like, hey, just and if you guys have to go because I'm rambling now, feel free. But yesterday I went and I helped my cousin move a trailer. He bought a 27-foot trailer. He lost his job like around the start of COVID, and he's planning on starting over. So he wants to, instead of paying rent in his apartment, he bought a big trailer. He found another friend who has property with a site to put a trailer, and he's gonna move onto his friend's property and rent from his friend for a while. Anyways, I had to move this big trailer, and when we got there, I found out my truck doesn't have all the right electrical wiring to communicate with the trailer brakes. So I had to install something called a brake controller that talks, like, you plug your trailer into my truck, and now my truck talks to the brakes on the trailer, and when I step on my brake pedal, and it has a little accelerometer, when it feels me starting to like tip forward or tip backward because I'm accelerating and decelerating, it'll decide when to turn the brakes on the trailer on. But I used all these skills that I learned in robotics that Evan helped me, like about wiring and correct wire gauges and what color butt connections for splicing wires together, what colors to use, how to crimp things. I It was really fun, and what was crazy is YouTube helped me. So one, I'm glad I watched YouTube because I was able to go buy this $70 part and within 1 hour have it installed in my truck, correctly wired, thanks to YouTube and thanks to robotics. And it probably saved my cousin a whole week worth of trying to find a different truck to get it across the mountain. So I don't know, I had a lot of fun, and it was all these little bits and pieces of skills that I picked up over the last few years. So anyways, stuff that you think, oh, this is kind of fun or interesting, or oh, this is boring, but my teacher wants me to learn it, maybe at some point will come into use, which is pretty impressive when it does. So you should be cognizant of all that and try and learn. And Keaton, you need to go get some exercise.
Thank you.
Yeah.
Exercise.
And yes, and Savannah, tell me about your track experience.
So it went really well, but I couldn't figure out through the recording process. Am I supposed to record? Like, is the person supposed to record me running all the way down the runway?
I don't think so. You can use, because you could attach pictures or video. So I kind of think like you could take a picture of the pit holding a tape measure and then just write down your mark. Again, it's like honor system.
Yeah.
So yeah, I think any legitimate documentation that you were out there doing it is gonna count.
Okay, but yeah, I'm so happy. I was surprised that I was able to get a foot under my best mark.
Nice.
Without any practice or anything.
Do you need do you need a longer tape measure?
Yes.
Okay.
I was trying to use like the kind that you use in your house and it's like metal.
Yeah.
I was trying to use that and it did not work out very well, but it kind of did.
Okay, I'll try and get you a tape measure. I'll see if I can find one, and then I'll maybe just leave it at a pit or something for you. I'll talk to you on Remind.
Okay, and then I can probably bring a rake from home.
Yep.
But I was just using my feet to rake it.
Okay. Hey, I know Arthur's gone. If you guys are still here, sorry for my rambling, but I'm gonna go, and I just want to show you the homework for this week. So this is mostly for Tyler and Vincent, but you guys should do it too if you haven't already done it. I mentioned it last week. I went in and I put in AP Classroom multiple question progress checks, and Savannah's turned in her attachments already. Because are you done with most of them?
I did all of them.
Oh yeah, so she just took a picture.
Sorry about that.
She just took a picture of her progress check. So I'll just pull up the first one. So there you go. So show me what you got, and then just attach it to your thing. Even if you don't get all 7 done, try and get them mostly done and attach what you can. I won't see you guys again.
So,
Yeah, I won't
with
see you
the
guys
progress
again till.
checks?
Oh yeah, go ahead.
With the progress checks, when it says like certain parts that I didn't do so good on,
Mhm.
can I get like questions for those like skills?
Yes. So what I can do next, I think, is I can assign more multiple choice questions that weren't part of the progress check. They gave me a question bank, so I can just pick like say 25 more multiple choice questions in the areas that you guys are like needing work in.
Okay.
So I will, once I start to look at these, I'll make some more assignments on AP Classroom that have a mixture of questions for you guys.
Okay, sweetie.
So, okay, and today's the 20th. Again, I think our test is May 14th, right?
Yeah.
So we're getting closer. I did see on Khan Academy, if you guys are really looking, they have AP Chemistry like study curriculum. So you can go through. There's videos. There's some questions that you have to type in answers for. So, and there's some articles to read, and it's all structured in the same format of a AP test. Although it is the traditional test where it probably is going to be a wide scope of things, but you can kind of take bits and pieces of it. It's a pretty good resource. So check out Khan Academy this week. Try the AP questions, and then we'll do this on Wednesday and on Friday. We'll have little lectures. So 10:30 Wednesday and Friday.
Have you guys noticed how many 20s are in the date? Kind of scary.
All right. Hey, and Keaton, I wasn't being mean. I'm just saying go enjoy the weather and go
I
for
understand.
a bike ride.
I might.
All right. See you guys later.
Yep. Yes.
Bye.
All right. Bye.